we are. So, hi and welcome to this session, and I'm glad that you're here. Do you know how horrible it is to watch yourself on video? Like, don't do that. So, yeah, in this session, we're going to talk about how to enable zero downtime applications and zero downtime deployments with Kubernetes. So, my name is Sebastian Daschner, born and raised in Munich, Germany. I'm very happy to be here. This is actually my first time, and I'm a developer advocate for IBM. I do a lot of Java things usually, but also enterprise software in general and everything enterprise projects need. So that also covers a lot of DevOps topics and containers, container orchestration, service meshes, and so on. So let's talk a little bit about that in the next few minutes. We're going to talk about disruptions. Disruptions can be in a wanted and unwanted way, planned or unplanned disruptions. And well, unplanned disruptions usually cause some user disruption, usually cause some downtime. But specifically, we want to talk about planned disruptions and at least mitigate them so that once we plan some maintenance or plan some update to our software, we do not impact our users. That's basically what it is about. And if we talk Kubernetes, Kubernetes is a container orchestration framework technology that has been built with production readiness in mind, right? So if you look into this technology, it comes with a lot of features that aim to be ready for production. So let's talk a little bit about that. The production readiness out of the box that comes with Kubernetes, and let's have a little bit look into that later, where we specifically want to pay attention to. So what does that mean? Which things does Kubernetes bring for us? So first of all, it comes with some so-called controllers, like replica sets or deployments that typically manage our workload. So deployments, or specifically replica set, are responsible for replicating your pods. And once a pod goes down, either in a planned or unplanned way, then it will be replaced by a new pod and all these things, so that you always have some workload there that is available. And it also comes with this abstraction called services. So all your applications are abstracted in these logical service deployments, such as microservices, that then load balance to your instances, right? Because you want to have multiple instances of your workload, for example, and then the service will load balance and distribute the load and make your workload accessible. In the same way, pods that fail will be rescheduled, and of course, and that's also a little bit the focus of this talk, we can enable zero downtime deployments by rolling update deployments, right? So once we deploy from an old version to a new version, then out of the box, what Kubernetes supports is that the new version will be made available without disrupting the old version, right? So you have a rolling update and not just a go down and come back up update that would mean some downtime to your users. So specifically, what I want to show you is, because slides are boring, I want to show some live demos. Is a deployment that is a very basic hello world application, more or less, that we want to deploy to Kubernetes environment and later on also to service mesh and Istio environment without any downtime. So I like coffee, so this is why I have a coffee shop example application that basically gives us a hello coffee response, and that I want to deploy on a Kubernetes environment. So where do we get a Kubernetes environment from? Well, we have tons of options to install that, right? So either Minikube locally on your laptop, or take cloud environment. I have to log in. It's funny. I use the IBM Cloud for a managed Kubernetes cluster. So to get one of that, and hopefully we have some network here, so we can use this. Yeah, this is how that looks like once you're an employee, and then we can log into clusters to this one and then see all the Kubernetes clusters that we have here. And of course, you know about this tool, kubectl, to manage everything here, right? So once we have this kubectl tool, we can manage our deployments and see what our Kubernetes cluster has, right? Kubectl give us the services, give us the deployments, or get pods. You can see that this cluster that I'm using here is deployed from the cloud, that this is currently empty, right? All right, let's change this. Let's deploy something here. Very quickly, just a poll. I think all of you are familiar with Docker and Kubernetes. Hands up. Most of you. Okay. So let's see. Then maybe just quickly, what I have here is a Java Enterprise application. Actually, it doesn't matter that much what you're running. I will talk about a few things that you need to keep in mind in your application, in your container, what is actually running. But other than that, from a Kubernetes perspective, it doesn't matter at all. Anything, for our case, that talks HTTP is just fine. I use Java, specifically Java Enterprise. This one uses a Java E8 application that is deployed to an application container. Again, doesn't really matter that much. So this is deployed and built as a so-called WAR file deployment. And then we have a Docker file that basically specifies how our runtime, well, looks like at runtime, right? So the whole binary, everything our application needs, that is specified in this Docker file. As you can see, that's not much. So basically what we have an application server as a base image. That makes sense, so we don't have to add all these steps ourselves, right? What does our application need in order to live? Well, our application, that's the one part we actually add. Then typically some application container or framework implementation, some JRE or JDK, right? In the Java world, some Java runtime, some optional operating system configuration, things like that, right? Everything you need in order to run later on in production needs to be here. So almost everything I just mentioned comes from the base image, and the rest, well, that's our application that we add. So that means we build this Docker image, and then we can run a Docker container. That's of course boring. We don't want to run that locally. We typically want to run this in our Kubernetes cluster. That means we have this YAML files. Who of you is familiar with this YAML definition? Hands up. Who knows YAML files? Who likes YAML files? Hands up. Oh, a few. Okay. So in this YAML files, these basically act as infrastructure as code definitions. We specify how our cluster looks like, right? The whole cluster, the whole environment. So not only one specific instance that we had in the Docker files, but basically we specify, well, which services we have. How does the deployment look like, right? And of course, for us, that means in a very basic way, we have one image, replica one, of one instance of that image. So we have later on one Docker container of this running instance here, and this is going to be deployed. All right, let's do this. Let's deploy the whole thing. Then we have a bunch of things created, mainly one service that is called Coffee Shop, and a deployment that is also called Coffee Shop, and then we have a running pod. Well, right now that's starting up, and then hopefully it'll be running. Let's show this on the right hand side. Every second we see the status of the pods here, and that's pretty much it. And once that is up and running, well, we can see whether we can access it from the outside. So let's get the IP address of our cluster, and then we can access Coffee Shop resources. That's a JAX-RS application path, and it's called Coffee. And it says Coffee. Well, great, right? Exciting. So we have a Hello World instance running on Kubernetes. Awesome. So what else we have is another image. I just changed the definition from 1 to 2. This is typically one way how we deploy a new image, declarative way of specifying what we want, the target state. So we change a YAML definition, and now again we throw it against the cluster. And then what happens, kube control apply. This is typically a command we use for that, right? Not create, not modify, no, apply. So whatever change we make or not, we just throw it against the cluster, and then the cluster itself, depending on the current state, will say, well, something changed or not, right? So the deployment changed. That means now we deployed a new thing. And this is the out-of-the-box behavior. That means what we do, we create a new container, but the old one is still running. So we create this new pod. The old one is still up and running and ready because, well, the new one is not ready yet. So that's the whole point of rolling update. I just don't shut down the old one just yet, because that would mean we will have some downtime. but we can still access our coffee, and then if we have the new version, we get this coffee mug, right? Wow, even more exciting. So that's version 2. And as you can see, well, this happened basically without a downtime, right? So we wait until the old pod is ready, until the new pod is ready before the old pod gets discarded. First question that I had, how does Kubernetes know once my application is, ready to serve some traffic? Well, initial answer is it doesn't. I mean, it can't, right? Because Kubernetes is just about running containers, right? It can literally run anything. It doesn't know about our Java enterprise application and when our application is ready, right? Like typically, enterprise application takes some time to start up. We might have a JVM that needs some time. We have an application server and so on and so forth. And for that reason, we have these probes, liveness probe and readiness probe, right? So the probes basically tell us, well, whether the container is in a particular state. Either it's alive or it's alive and ready. What does that mean? Well, liveness probe basically tells us whether the container is still even alive, right? Even up and breathing. So if that is not the case, then we can immediately go and kill the container and start a new, kill the pod and start a new one. If the container would not be running anyway, well, then this obviously means it's not alive. So that's implicit, but also for some reason, if our container crashes or our application crashes in a way that it will not recover, then we could build in a probe that tells, well, I'm not alive anymore. These probes are very flexible. We can execute commands, we can fire up HTTP requests against the local host, basically. We can check whether some ports are listening there, whatever that means, right? It's very flexible since we can run virtually anything in our technology. But what's a little bit more interesting is the readiness probe here. Because the readiness probe is the notation whether our workload is ready to do some meaningful work, right? And this quite varies from being alive or not, right? Because if our application is just starting up, it's not ready yet. We must not route some traffic to it. That would be bad. But also we should not kill it, right? Because it's just starting up. It's normal that it's just starting up. So that's a totally different state. And for that reason, we say we define a probe, and only if that returns true, then we know it is ready here. And in this case, I return, well, a health check. That's going to be there once the application is deployed. Again, very specific to whatever you're running, but that basically means this is now ready. All right. So you saw it. That works without any downtime. So we're done, right? We might have a little bit closer look. What I just did is, well, I fired 2 or 3 requests. And it looks quite nice. But if we dive a little bit deeper, well, we might have a closer look how actually the deployment behaves once it is, well, it's under a current deployment. So what I do, I set up a load test, and what I have here is, well, my Kubernetes cluster, and my laptop is outside here. This is where I sit, and we have this coffee shop and, well, some Ingress resource. And what I have is a load test tool called Fortio. I could use any tool that just fires up a lot of HTTP requests in my case, but that one sits inside the cluster. Why? Well, if you sit inside of a cinema, you should not rely on the network. So I don't want to flood the network with a lot of requests if I want to put a heavy load on it. So this is why it sits inside the cluster, but uses the same external address to take the ingress route, in our case, to basically test user behavior, right? Because it's a different thing if you redeploy an application that's currently under heavy load, right? This is just my laptop, what I did. But in production, it looks differently. So what I do, let's have yet another terminal, because that's so funny. We can fire up a test. So this one, curl test, only issues 1 command. Okay, that's great. So this works, and what it does, I can fire up this load test that uses this Fortio pod that actually, you already saw it, that resides inside the cluster and then fires up the load test and, well, fires up a lot of load. And what we can do, control port forward. Fortio, what's that, 8080? Then we can have a look at it actually. There's even a funny browser. Well, now it's empty because there is yet a load test to come. And once we have the result that runs for like 40 seconds, then it shows us the result of the response times and of course response codes. I'm not that interested in the overall load test as in performance factor or aspect here. I'm more interested in, well, what does it give us? And I expect 100% uptime. Well, because there's no deployment happening, right? It's just idling around and it should handle a little bit of load. All right, but now if I redeploy, or if I go from version 2 back to version 1, I mean, it doesn't matter. Deployment coffee shop, and then fire up that load test again, then what I would expect is, well, also zero downtime during the deployment, right? So again, we can have a look at the current pods. Same story here. The new pod is being created, and that is currently starting up. We wait until that is up and running, so we wait for the readiness probe to get ready, and then only once that is the case, then the old one is parse non-OK code 502. Oh, that doesn't look that good. Well, it's a live demo, right? Everything can fail. So let's see. Let's see what it says. So the old pod is already gone, and now it looks good again. It doesn't throw additional errors. The new pod is now up and running, and hopefully, well, that gives us a response. Yes, looks good. And you know, 99.8% uptime, and we could round that down, and then it's basically zero downtime, right? Agree? So we can go home early? No? Too bad. So although it promised us zero downtime and production readiness, it's not quite zero downtime, right? Apparently. If you just go for an out-of-the-box approach with a readiness probe, which is obviously a good idea, but it's still not quite zero. So let's have a look at what happens under the hood actually. So I have two scenarios how I could connect to my services. The first one is obviously I could use any service that sits inside the cluster and just connect to the other one, usually via cluster DNS, or I can use this Ingress approach, and then of course depending on my Ingress implementation. Let's go for the service route first. A little bit more ASCII art here. What we have is the Fortio load. On the left side, it could be any client that uses cluster internal resolution. And then we use the DNS or the service VIP, service virtual IP, to look up the service. And then basically using this virtual IP to ending up at one running instance. So this uses this IP table routing and Linux black magic to end up at the actual instance, at the actual pod. Each and every pod has a unique ID inside the cluster. And, well, what happens if we want to redeploy that? If we redeploy, that means our service routing, doesn't matter how many instances we have, needs to be routed to another instance, the new one that is just starting up. That's a good idea, and how that works is we have a component called kubeproxy that runs on each and every node in our cluster locally. That is responsible for talking with the higher level Kubernetes API, the endpoints API, and watches it for what's currently the current state, what's happening inside the cluster, and then using and installing these IP tables to route accordingly, depending on the current state, right? That sounds good, right? Makes sense. But since we're in a highly distributed environment, what happens is that this, as you can read, watches, this happens in an asynchronous way. So we see what updates there are on the Kubernetes Endpoints API, and oh, this service just got a new pod, and that one is now being discarded. Oh, then let's better update the IP tables, right? But again, asynchronous. We don't know yet whether there's already some traffic coming in to that's supposed to be routed to a new pod and not the old pod again. Because what happens is, as soon as the deployment says, now the old pod is ready to serve some traffic, we can shut down the new pod. Sorry, I meant to say the new pod is ready. We can shut down the old pod, and in the same way, it's being terminated and the endpoints object is updated. But then, depending what happens first, because asynchronous, that might be updated after the pod is already being terminated. It's already being shut down, and then it won't accept new requests, and then we see some downtime. Similar story if we use an ingress. There are multiple implementations. I use the Nginx Ingress, and if you ever configured Nginx for yourself, you might see this actually. You can configure some upstream servers, it's basically some targets, and that's what happens. So it actually doesn't use the services directly. It also goes for the service endpoints. So service and endpoints is a one-to-one relation typically from the service, like coffee shop that we had, to the endpoints, which is a list of instances that currently serve that coffee shop service, the one pod we have. And once that list changes to the new one, to the new IP address, well, the Ingress also watches for these changes and then updates its logic correspondingly. And then we, well, basically see the same effect. Why? Because watches asynchronous as well. And then, well, it depends what happens first. All right. Sounds reasonable, or is at least an explanation, but how to mitigate that? How to get some zero downtime now? What we can do is go for an approach where we say we have this rolling update, and we have a pod that is now ready, pod 1, where we want to route to, and the other pod is what we do. We introduce like the functionality of a so-called lame duck, and at the same time we label that runtime now not ready, so try to take it out of the list of endpoints. But at the same time, we just not yet want to turn it, shut it down, because then it might still be able, or it is still be able to respond to some traffic, to respond to some requests. So if some unlucky request still ends up at the pod, it also will be responded. And how to do that? Well, there are multiple ways. One way is these containers have a life cycle. Some lifecycle hooks where we can actually hook in, and there is a pre-stop hook where we can do some actions. And what these hooks are, they define some actions. For example, please execute this following action, which happens synchronously. So that will be executed before the pod is actually being terminated, before the SIGTERM signal is being sent to the container. That means if we execute any command here, for example, what's a good way to be productive and to solve problems sometimes? Just sleep. If you can't solve a problem, just, take a nap, and then the problem typically solves itself. So that's what we're going to do here. No kidding. We actually define please wait in a synchronous way. Why? Because at the same time, like I just said, the pod is supposed to be terminated, and it will be marked unready and being taken out of the endpoints object. And now what we do, it will be taken out of the endpoints object, and we will fire up that lifecycle, the stop routine, right? But before that, we have the 20-second, depends what you want to do, wait period in a synchronous way before we actually send the termination signal. So in this case, if we do that, let's apply this first. Then hopefully, well, we have another deployment happening. Let's first of all start up this pod with the new notation, and then after that is fully up and running. What we can do is deploying that in a new version. So that is now up and running. Now I can apply it again, and at the same time fire up my load test again. And then what we will see is that it behaves a little bit differently. So we fire up the load test, and now same story. The new pod is starting up and becoming ready. So just as before, but once it is ready and ready to serve some traffic, what happens? It behaves a little bit differently. The old pod is now being terminated. Well, but you see, it's not disappearing just yet. It's still there, but it will be removed from the endpoints object. So now your workload might already be served by the new one only, and we wait a little bit more until it's terminated, until we can be sure that no request is ending up there, and then it's actually being terminated, and we see 100%. Okay, looks good. So that's one way how to solve it, apparently. Now let's look a little bit further. That was a Kubernetes only approach, how to do that and how to mitigate this issue with lifecycle hooks. Another issue that appears once we use the service mesh technology called Istio is that, well, we have a runtime running in a little bit different way. Well, I can show these graphs, but they're actually not that interesting. So what we would see here in our load test result, this is a positive result, you know, with a nice distribution, and there, well, you cannot even see the interesting part. It says so and so many % errors, and what we want to have is, of course, no error. Well, what we want to have a look at now is Istio, general service meshes. Service mesh technology that allows us to do a little bit a few more things. For example, advanced traffic routing or added observability without changing our applications inside the mesh of our microservice deployments. So what I also have an Istio cluster running. Let's use this Istio, and that one is currently empty. So let's deploy something there. And now let me switch branches. Yeah, I don't care. Now we have a similar approach with our Istio resources that are now deployed to an Istio cluster. So what we have, deployment deploy. What we have is a different approach where, you know, in this Istio environment, we always have 2 running containers per pod. Because of the sidecar container, I explain a little bit of that in a second. And then what we can do, we can have some advanced traffic routing. But first of all, if we just want to have the same approach that we just did, zero downtime deployments by migrating to a new version, then, well, let's check this out. We have a slightly different IP address for our cluster, coffee shop, resources, coffee, right? Same story, coffee, boring. And now if we would simply deploy that in a similar way like we had before, well, let's check this first. We again have our curl test. One thing to keep in mind that actually might change in a future version. If we take the same load test scenario and want to access the cluster from the outside, it does not work out of the box. Why? If you know about Istio, these Istio proxies out of the box prevent any external traffic. So what we have to do, and you can have a look at the further Istio configuration, and at the end I will provide you a link where you can find that. We have to add the external address that we want to reach. In this case, it's just an example to be able to reach, well, our own cluster. Otherwise, it will not allow us to do that. Service entry. And once that is the case, we can actually access our own workload from inside the cluster. So now the curl test works, and then we can fire up our load test as well. And then I can deploy this deployment YAML that I just wanted to update, right? Let's fire up the load test first, and then deploy our new version in the same way that I just had for Kubernetes. But then, well, what we might see a slightly different result that we also want to take into consideration. So now, same story, we'll fire up this load test that now uses the Istio resources. That means these proxies and gateways that are deployed in our cluster. I will provide you some resources, how you read that further. Parse non-OK code, this time 503. Funny. Another error. This time a little bit different. Again, we still have the same goal. We simply want to deploy a new version without disrupting any users. As in not losing a single in-flight request and a single TCP keep alive connection, right? But it doesn't seem that easy. Let's see what happens now. What I did, I used this Istio cluster. What it is a service mesh of interconnected microservice deployments where we deploy these sidecar containers, these proxy containers, alongside of the pods. So what it is here is our pod, such as in this case it would be a client like a Fortio, where we have the main container, the actual application that is running that wants to access another service, and a proxy. And the application transparently always uses this proxy to make the connections. And what the proxy does, well, it does a few more things. For example, it adds some resiliency on its own. So it has some outlier detection, what happens if some external system becomes unavailable, and so on and so forth. It can add some own timeout, retries, and all kind of things. And also it manages its own list of endpoints, where to go to for specific routing. Well, and that's basically the issue, because somebody needs to update that list. And as you can see, there is so-called Istio pilot, plain pilot component that configures all these proxies, where to route to, and, well, same story. It watches the Kubernetes Endpoints API to get this new routing, this new state. And again, we have a distributed system where in an asynchronous way, we're gonna update all these workloads. All right, that's not that great news, because now similar issue. What we're gonna do? Well, we cannot here kind of wait, because, well, we simply need to wait for the proxies to be reconfigured, and before we can do something with the pods. For example, before we can terminate the pods. And in this case, what we are actually going to do now, we go a little bit different ways as we just had before with our sleeping trick in Kubernetes. And what we do, we define some actual and explicit steps when to deploy what. Basically what we're doing this blue-green deployment approach in a more sophisticated way using the Istio traffic routing. And if you know about the traffic routing roughly, how that works is we can define subsets of services that are defined by the labels. So instead of just saying coffee shop, and we have one instance of the coffee shop and then a newer one, once that is being redeployed right now, what we can set up is another subset, like an own version of the coffee shop that might run longer than just the small duration during an update, and then route accordingly from one subset to the other one. How that is configured is in so-called virtual service and destination rule resources. These are resources that come with Istio, and they basically look as follows: that we have a routing here where the destination rule defines the routing to the coffee shop. This one is extremely boring. It simply says everything that goes to the coffee shop, well, route to the coffee shop, define these versions subset. And here in the virtual service traffic routing, everything that comes to the coffee shop, route to, well, the coffee shop. Here's same story here. So what we can do, we define the subset label as part of our Kubernetes deployment. All of the pods come with v1. And what we simply say is, well, then, during the deployment, first of all, set up two subsets. Only that, define these two subsets. And we have a second Kubernetes deployment that just is starting up. And the old one is not disrupted at all. It's still running. And the old Kubernetes deployment is still there. And then what we do, once the new one is up and ready, well, we simply switch the traffic from v1 to v2. And then we can take down the old one, the old subset, and then delete the old Kubernetes deployment that then deletes the pod. Make sense? And all these redeployments, well, will work on the Istio proxy side because it's reconfigured, and we can wait until all of the requests, well, basically are done and rerouted. However, we certainly do not want to do that in a manual way like I just did, but we want to automate that. So again, same story. We define multiple subsets. That's the initial state. We have one subset where we route all the traffic to. Then we can build up a new deployment of pods that are deployed with version 2. We fire up a second subset, and then ultimately we make that switch, and that is the actual deployment where we reroute the traffic, and the old one is still there. So, you know, that doesn't matter why that's being reconfigured, and only then we can take down that as well, and then it works on this side. So what we can do is deployment exec. So I have, or just for demo purposes, a script that sets this up. So please deploy this from version v1 to version 2. And what it will do, here you can see this has a different name, v1 and v2. That's the name of the Kubernetes deployment. So that is part of this. And then what it does, it waits until the new one is ready and up and running, and the old one is not touched from that at all. The deployment is not even changed. And what is that? When that is the case, it is just being rerouted, and then again we wait a little bit, and then the old one is taken out of traffic, and we take down the old deployment. And in that way, we can deploy that with, let's test it again, roll back. Oh god. Version 2, version 1, image 1, fire up the load test and deploy. Let's hope for the best. And then hopefully that works without losing a single in-flight request. As you can see, this is now a little bit more sophisticated approach, and also this is the route we want to take if we now think of continuous delivery, right? Because what we do, we want to fire up a proper continuous delivery pipeline where we actually define these steps. And not only these, but also furthermore steps, because Istio, in that example, or whatever technology we use, it allows a little bit more complex traffic routing. So instead of just saying go from version 1 to version 2 and back, what we can also do is define some A/B testing or canary deployments where we say, please route so and so many % of the workload to this and this version. So what we then could do, what is a very good idea, in a continuous delivery pipeline is defining a process that is now being automated of, for example, saying, please deploy that new version and then route gradually 1% of the traffic, 5% of the traffic, and increase that rate. And at the same time, have a look at your monitoring, whether that new version immediately blows up with errors or such, where you actually could roll back automatically as well without disrupting too many of your users, right? And then ultimately, you'll end up hopefully with 100% downtime as well. So that's the more sophisticated approach, I'd say. At the end, I'll show you where to find these resources. What else to take into consideration? Now, again, dial back a little bit more on the low-level terms, on container terms. Of course, we want to gracefully terminate the pod. Well, in this case, if we go for a blue-green deployment, it actually doesn't matter that much whether we simply kill the pod once there's no more traffic incoming. But in any way, that's a good idea in terms of resources, that we gracefully shut down everything, for example, close database connections and so on and so forth. What that means, typically, we want to send a terminate signal to the running process, and then, depending on your workload, what you're doing, all Java enterprise containers, for example, gracefully shut down, then handle all of these open connections and so on and so forth, and that works. The only thing you need to take into consideration is how to run it in containers, because depending on how you start up your application, for example, if you run a bash script that then starts up some workload, it might not handle these signals correctly. So make sure that works. Easy to test. If you fire up a Docker stop or hit Control-C in a running container, it should shut down immediately. If it ignores the signal, then after 10 seconds it will be killed, but that's a bad idea, right? Because that's a sick kill, not a termination. So gracefully test that. Another interesting idea is so-called pod disruption budgets that comes from Kubernetes. It specifies the disruption budgets. That means even if your sysadmin or your DevOps, another DevOps engineer, or however you call them, wants to do some cluster maintenance and temporarily take down a node, if you do that immediately, then it would just kill all the pods that then need to be recreated somewhere else. But if you define a disruption budget, you actually cannot take down the node until all of these important pods are being rescheduled somewhere else in the cluster, and it will block until then. So have a look at these. Simply search for pod disruption budgets, and then these will be considered by the appropriate commands. So as a takeaway, always properly verify and test your deployments, and also verify it as if you were running in production, and ideally do that in production and see what the impact is of your deployment, and then try to mitigate downtime. Typically that means some variation of a blue-green deployment approach. And in any way, also very important thing to consider, once you have any approach of blue-green deployments of zero downtime, then you always have to consider N-1 compatibility for external systems and mostly for databases, because you use the same database scheme for multiple versions at the same time. even if it's just for a short amount of time. So make sure these versions are compatible at the same time. That's a huge topic on its own, and there are resources how to do that, but you want to take that into consideration. And of course, don't do it yourselves. Use the computers how they're meant to be. Use automation to automate and properly test that. That's all I have for now. I hope that was helpful. Thank you very much.